I'm the next speaker. So if you do not know me by now, my name is Erik, and I'm assistant professor of psychology here at Hamline University. I also hold a secondary research appointment at the University of Iowa, Department of Neurology. I've done postdoctoral research with Dr. John Cacioppo at the University of Chicago and Nancy Grayson at the University of Iowa. My work broadly examines the functions of the prefrontal cortex and its role in mediating doubt. Okay. So I just want to thank you all one more time for attending, and a deep felt thank you to everyone that made this event possible. The aim of my talk is to discuss some of my investigations into the neural substrates of disbelief, and to conclude with an admittedly rudimentary, can't get it all the way, neural circuitry model of belief and doubt. All right. So let's start here. Again, in the early 90s, Dr. Daniel Gilbert came out with a series of papers discussing the psychological mechanisms of belief. He contrasted two philosophical perspectives, the Cartesian view and the Spinozan view. The Cartesian model suggested that mental representation or comprehension of some proposition is separate from assessment, belief or disbelief in that proposition. In this view, we first understand something and then we either choose to believe or disbelieve it with the voluntas, Descartes' will. Okay. Our Baruch Spinoza argued that this wasn't the case. That mental representation or comprehension is the same process as belief. And he argued everything we comprehend is initially represented as true. Okay. Now, we can perform an assessment process and disbelieve a proposition with a secondary psychological operation. This can only occur after comprehension and mandatory belief. Now, what's remarkable about these two models is that given unlimited processing resources, they will produce identical belief outcomes. However, when there is a disruption of processing, as in the case of distraction, okay, early stage products can be output prematurely. That is, the products of the representation stage can be output in the event of assessment disruption. This means that a distracted Cartesian system would show preserved comprehension, but no tendency toward belief or disbelief, and a distracted Spinozan system would show preserved comprehension and belief, but no tendency toward disbelief. Okay. This is all well and good, but the tricky part here is that we often don't know how effective the attempt to disrupt assessment has been. Okay. It's hard to know exactly when to distract, and what amount of distraction will disrupt assessment but not representation. Moreover, there's nothing to prevent a later reanalysis in some of these studies of an assessment stage if, after the distraction, the subject can remember again the proposition. And this seems very likely in situations with strong background. Thus, negative results against Spinoza may be the product of poor experimental design rather than evidence against the model itself. But what we really need here is an experiment that could give positive results for either model, okay? And some method not dependent on the vagaries of resource depletion. All right. So what if we could find individuals with more of a permanent disruption of the assessment stage of processing? So at the University of Iowa, where I did much of my graduate and postgraduate work, we have the world's largest database of individuals with focal brain damage. These are circumscribed lesions that usually are produced from strokes or tumor resections. We realize that if this brain damage to particular neural substructures could disrupt belief processing and grant evidence for competing belief models. So what's needed here is a brain injury that left the representation stage preserved, but specifically disrupted the assessment stage. Thus, the Cartesian model would be supported if a lesion to a particular brain area disrupted assessment and rejection, perhaps Descartes' balloon toss, the will here, but left comprehension preserved. And the Spinozan model would be supported if a lesion to a particular brain area disrupted unacceptance, but left comprehension and acceptance preserved. That is, we should find a general credulity toward novel propositions. Specifically, the secondary doubt process would be disrupted here. But what brain region, if damaged, would lead to a disruption in assessment? Well, as I mentioned before, my mind immediately went to the prefrontal cortex due to several interesting symptoms and deficits we see following damage. On first encounter, just to give you a little flavor of what these patients are like. On first encounter, these patients often seem really normal. Okay? There was a reason that we initially called the frontal lobe the silent lobe. This is an MR patient 3534 who had a meningioma tumor resected in her ventral medial prefrontal cortex. The black part here, not good. Damage, okay. General neuropsychological testing with prefrontal cortex patients often show normal IQ, normal memory functioning, normal visual spatial functioning, normal language functioning. Okay. However, more precise tests do find this strange, motley assortment of interesting abnormalities in these patients. And these are the things that really tipped me off all those years ago. So I'll describe some experiments we've done with these patients, and then we'll return to two interesting classes of symptoms. Okay. One of the first studies we performed to examine this question, we gave lesion patients negazine ads that had been deemed deceptive by the Federal Trade Commission. We asked them, one, whether they believed the deceptive aspect of the ad, and two, how likely they were to purchase the product if it became available at a nearby store. So this is a lesion overlap map. This is not an activation map. How many graduate students that come up on a poster? Oh, they call it activation. This is lesion overlap map of the 14 patients that had damage to the prefrontal cortex. We also include BDCs, which are brain damage comparisons. These are patients that had brain damage to other areas that are not the prefrontal cortex. And healthy adult comparisons, HAs. Now we reasoned that if we gave participants information that normally tends to engender doubt in most people, this should be reduced in prefrontal cortex patients. Indeed, we found that the prefrontal cortex patients were most credulous to deceptive ads, and they were most likely to endorse purchasing the product when it became available. So, prefrontal cortex patients are more credulous to subtle, deceptive information that normally elicits skepticism in healthy individuals. But if this is a true doubt deficit, shouldn't they hold more extreme beliefs? Maybe propositional beliefs that exist in the social milieu that are readily doubted by some people. Therefore, we thought religious beliefs might be really interesting and particularly valuable in that they're common in the marketplace of ideas, they're held to varying degrees, and they're not really directly falsifiable. So if the prefrontal cortex is critical for the retroactive doubt in the Spinozan model, then prefrontal cortex patients should, on average, have more religious beliefs and be higher in religious fundamentalism. And indeed, we found the prefrontal cortex patients had the highest religious fundamentalism compared to BDCs, healthy adults, and we also included a medical comparison group. These are patients that had a life-threatening medical event that was non-neurological in nature, just in case being in the hospital and having a bad thing somehow changed religious beliefs. But no, our prefrontal cortex patients were way above everybody else. Thus, it appears that on average, prefrontal cortex patients are more likely to hold fundamentalist and more extreme religious beliefs. Okay. However, we needed a more decisive test to show that prefrontal cortex damage increases credulity generally. We need to provide prefrontal cortex patients with novel information and have them explicitly disbelieve some of that information. Thus, in my dissertation, we did this. So I examined belief and doubt processing with 4 groups. So patients with bilateral damage to the prefrontal cortex, these are in red. Here's a single overlap map of all the groups. Patients with superior parietal or superior longitudinal fasciculus damage. The fasciculus is the major white matter tract that connects the frontal and the parietal lobes. This is in purple. Patients with other brain damage outside of the prefrontal parietal circuitry. This is in green. These are our BDCs. Okay. And the darker colors here are more overlap of the lesions. And obviously, we also included healthy adults at varying age. We gave our participants the dispositional judgment task. And this is a task modeled off of Dr. Gilbert's 1993 criminal judgment task, where they read 4 stories presented sentence by sentence. Embedded in each story was a series of explicitly labeled true or false statements, which was cued via the text color. Okay, for white for true, red for false. The secret here was that the false statements were designed to sway the opinion of the critical trait of the protagonist if it was mistakenly believed. So on the right is Mike's story, and the false information appears in red here. Okay, and if participants mistakenly believe this false information, they will think that Mike is more intelligent. Okay, and again, we're cueing them, we're telling them over and over, false information, or red information is false. False, false, false. Don't let it influence your judgments, etc. Okay. So they read these stories. Then the participants judged the protagonist on the critical trait, and here would be intelligence for Mike. And finally, the participants performed a recognition memory test for the details of the story. They answered true, false, never seen. Got a couple foils in there. Thus, here we should find a definite DJT recognition memory test pattern after lesions for the belief models. Lesions disrupting a Cartesian system should show increases in both true as false errors and false as true errors. So they should have an increase in both tendency to misremember true information as false, and an increase in the tendency to misremember false information as true. Whereas lesions disrupting a Spinozan system should show increases in only false as true errors. But we should find no lesion that increases true as false errors. Here they should show only an increase in the tendency to misremember false information as true. As it turns out, damage to the prefrontal parietal circuitry, in red and purple respectively here, dramatically increases false as true errors, but does not increase true as false errors. So this result is specific to the prefrontal parietal circuitry, as our brain damage comparison group did not show these increased false as true errors. This graph shows all the participants' false as true errors in diamonds, okay, and true as false errors in circles. So this is everybody that participated. Okay. The healthy adults are on the left, so all these are healthy people. I don't know what's going on with these people. But the light blue line here is the 0.33 chance criterion. So you're at chance with errors here. Okay. If you're at above this, we consider this individual to have a deficit in disbelief for false as true errors, and a deficit in belief for true as false errors. Okay. And notice that while a substantial proportion of our target patients were above this criterion for false as true errors, a lot of people up here, okay, no one was near the criterion for true as false errors. All the circles are below this line. So the amount of patients that we sampled, the amount of patients we did, no one ever showed up to 0.33 in terms of true as false errors. Other results from this experiment show that false as true errors are due to a belief bias and not a guessing bias. Okay? First, false as true errors strongly correlated with other beliefs and behaviors indicating a general credulity of information. The dispositional judgment of the protagonist correlated very strongly with false as true errors. And why would there be this strong correlation if participants were merely guessing truth? Rather, the evidence suggests that participants with high false as true errors actually believed the false information was true. True as false errors also strongly correlated with some orthogonal measures. We had a measure of cognitive consistency, which one might expect to be high in an individual that has deficit falsifying information. This measure also strongly correlated with false as true errors. False as true errors also correlated with some belief measures that many people might reflexively doubt or disbelieve, so-called epistemically suspect beliefs, such as religious fundamentalism, talked about that, ethnic prejudice, homosexual prejudice. We made a couple of other ones that we can discuss later. Thus, damage to the prefrontal parietal circuitry increases credulity to novel, explicitly labeled false information. Overall, this finding is supportive of the Spinozan model's view of comprehension with mandatory belief, followed by secondary retroactive doubt that's produced by a separate mental process. However, one limitation here is that we did not have perfect lesion coverage of the brain, so it does remain possible there are lesions to areas not sampled that can show dissociation between comprehension and belief. And yet, once we start viewing the prefrontal cortex central function as doubting, many of the weird symptoms we see after prefrontal cortex damage can start to be explained. This is why Dr. Gilbert's paper was so important to me. The prefrontal cortex, as a disrupted Spinozan system, really could address these odd classical symptoms. So I'm just going to discuss two of them here, maybe two of the most relevant ones. Okay? So first, after prefrontal cortex damage, we see pathological depletion, which can be described as honest lying. Okay? Here, patients provide information that is obviously false without intending to lie. They truly believe their misreports and will produce consequential actions based on those beliefs. And as you might be thinking, the symptom has a lot in common with delusion, okay, in a psychiatric sense. So this very striking symptom becomes easier to explain as a disrupted Spinozan belief system. If we posited imperfect memory search, that returns both accurate and inaccurate memory elements, and of which relies on the prefrontal cortex to act as the memory editor. Of course, this is now the canonical view of memory retrieval. The other symptom we often see of the prefrontal cortex damage is called perseveration. It is defined as the continued repetition of a learned response in the face of negative feedback. To get a feel for this, let's examine this in more detail in a task that patients often show, prefrontal cortex patients often show perceptive errors on. This is the Wisconsin card sorting task. Okay, in this task you're given 4 reference cards with different shapes up here at the top, okay, and colors, and a comparison card, okay, at the bottom. And the object is to correctly match the cards. However, you're not told how to match them. Okay. There are 3 card attributes which could potentially be correct: number of objects, shape type, and color. So let's say you start off by just guessing color. So we have this as our comparison card. Maybe we'll go with red, go with 1, okay? And get some feedback. Positive feedback. Woo! All right. Let's do another one. Color worked pretty well. Let's go with color again. 3. All right. Woo! Do another one. Color. Obviously, this is color. What? Come on. Perfect. Easy. Why are we doing this test? It's so simple. All right. Let's try this again. Got to 3. Oh, what? We got some negative feedback. Okay, never told. What is supposed to happen here? Okay. So in this task, after an association between attribute and positive outcome has been made, the contingencies of the task change, and the critical measure is how many trials it takes for subjects to switch to the new correct attribute. So let's say we get another one, okay, and we'll just stick with color. I don't know what the heck just happened there, okay, and we get another negative feedback. Okay? We call this a perseverative error. And Brendan Milner was one of the first to notice that prefrontal cortex patients make many more perseverative errors on this task. The more recent work has definitively shown that this is a specific problem it's a specific failure to use negative feedback to inhibit prior learning. So you have to learn first, and then they fail to use the negative feedback, the incorrect, to change their behavior. Moreover, in tasks where prefrontal cortex patients don't need to switch, but simply need to stop responding to a stimulus that isn't producing a reward anymore, they are much less likely to stop responding than healthy individuals and other brain damage patients. Okay, does anyone know what this is called? There's a very specific term. We call this extinction learning. Thus, perseveration is really a failure to extinction learn in disguise. And as my general psych students, hopefully a couple of them are out there, should know this very well by now, Pavlov himself was one of the first to show that extinction learning is new, sometimes weaker, inhibitory learning specific to the original association. He found spontaneous recovery, but the mere passage of time could reinstate the conditioned response. The thing that got me so excited 10 years ago was that if we thought of the attribute learning in the Wisconsin card sorting task as a belief, which then becomes falsified by negative feedback as a disrupted Spinozan belief system by prefrontal cortex damage. So a disrupted Spinozan belief system by prefrontal cortex damage would explain perseveration. Okay. And more than that, if we can understand the neural circuitry behind extinction learning, something investigated with many animal models, perhaps this would open an avenue for the neural circuitry of doubt or disbelief. Suddenly something very interesting and important was very attainable here. Okay? Another key finding, which is often overlooked, is that there's a tight correlation between perseveration and confabulation. One begins to improve after brain damage, so does the other. So as one improves, so does the other. Okay. And more than that, a recent study examining spontaneous confabulators found all of them to be extremely poor at extinction learning. This is not perseveration, this is straight at extinction learning. So this might hint to us that the symptoms are caused by the same core problem. And elsewhere, we've argued for a unitary common function supplied by the prefrontal cortex. However, I'm not going to rehash that here. Okay, let me get to the fun new stuff here. My argument is that the prefrontal cortex is critical for doubt. But of course, this doesn't mean that the process of doubt is only dependent upon the PFC. Several brain areas play key roles here. So with the remainder of my time, I'm going to try to stitch together a plausible neurocircuitry model of disbelief. This will be necessarily incomplete, and some of this is very admittedly speculative. I think there's enough data to start to form the outlines of how this disbelief might work at the neural level. Specifically, I'm going to focus on 5 critical areas. Okay, and I know there's a lot of brain terms here, but I'll go slow. Our prefrontal cortex, okay, the amygdala in the medial temporal lobe, okay, the ventral tegmental area, or the VTA, the midbrain, a fascinating tiny little structure called the habenula, just above the posterior commissure, and cortex posterior, the posterolatic fissure, or the central sulcus. And this will be kind of a stand-in for all cortex that's not part of the frontal lobe. Okay, so let's start with the prefrontal cortex. So we know that damage to the prefrontal cortex causes impairments of extinction learning, as shown in humans. We also see this in prefrontal cortex homologs in rodents and other non-human primates. We have found cells in macaques that continuously fire when a reward is expected but not delivered. These cells will sometimes continue to fire until the next trial. Here the vertical lines represent action potentials from the prefrontal cortex neurons. So rodent work on extinction learning has often used fear conditioning with an auditory tone being paired with foot shock. This will cause the rat to elicit measurable fear responses such as freezing behavior. So extinction occurs when a CS, or conditioned stimulus here, and here is the tone, is presented without a foot shock. Lesions to the prefrontal cortex impair extinction learning, and stimulation of the prefrontal cortex strengthens extinction memory. So in extinction of fear conditioning situation, how does the prefrontal cortex reduce fear responses? Okay, for that we need to examine our second neural structure, the amygdala. Okay. The prefrontal cortex sends excitatory glutamatergic projections to specific cell groups in the amygdala. Now to explain this, I need to zoom in on different cell groups. However, I promise not to be too detailed here. This is a coronal section of the amygdala. Okay? There are 3 critical cell groups for fear conditioning: the lateral amygdala, LA, the medial part of the central nucleus, and these really special cells that are dark in the stain, the ventral intercalated cells. Okay. The medial part of the nucleus produces the output to the brainstem and hypothalamus that acts to increase freezing and other fear behaviors to the tone after fear conditioning. The LA is the input zone of the amygdala and sends projections to the central nucleus for fear behavior. Information from the auditory cortex converge with pain information from the thalamus and somatosensory areas on cells in the lateral amygdala. And a really cool recent study has shown that long-term potentiation, LTP, is the critical mechanism by which a specific conditioned stimulus can be produced. So there's a strengthening of synapses carrying specific tone information, which then can produce fear-related behavior on its own. So the key for extinction learning is that it can reduce the fear behavior without erasing the original learning. That's, again, Pavlov, right? Indeed, this is what we see with prefrontal connections to the amygdala. Right? So the prefrontal cortex connects to these intercalated cells that then send inhibitory GABAergic projections to the central nucleus. Thus, these short GABAergic cells directly inhibit conditioned fear behavior without erasing the original learning. And this is driven by excitatory projections from the prefrontal cortex. Of course, the amygdala wouldn't mediate all extinction learning or doubt, only for behaviors driven by the structure, in this case, fear conditioning. But the remarkable thing is that this gives us a roadmap to find other similar circuitry for extinction learning and doubt. Maybe to things like propositions, for example. This is all well and good, you say, but how does the prefrontal cortex neurons know when to fire? to mediate extinction learning. So let's try to navigate these upstream waters a little bit. So to set this up, I think we need to think more deeply about what is happening when we encounter false information. I'm going to present you with a sentence word by word on the screen. Please read it. Referring to oceans again. Okay, what do you do here? As long as you're paying attention, you are actually predicting the word Pacific. Okay. You weren't just passively reading the information. You were actively predicting the next words to come. That's why we think we can finish our loved one's sentences. And why we're so quick to know that cow comes after how now brown. You're much quicker to arrive at Pacific than other words given sentence constraints. This is, of course, the notion of closed probability psycholinguistics. But what if the last word differed from your prediction? Okay? What if it was salad? You'd be predicting Pacific and get the word salad. Okay? Well, 400 milliseconds after the word salad would be presented, you would record a negative deflection on ERP if you were to test with EAG. Right? It gets really interesting when I don't just show you something nonsensical, which is salad, but something false. So same task here, but this time the last word is Atlantic. This, of course, is just simply wrong, but the interesting thing is you will still produce the same negative deflection on the ERP 400 at 400 milliseconds after seeing Atlantic. It's the same thing. Right? It doesn't matter if it's weird, it's wrong. It's against your prediction. And of course, the less you can predict the word, I don't know how many people that know the tallest mountain in India is, okay? Whether because you don't know it or you cannot retrieve the current knowledge, again, this is dependent on memory search, the less the 400, the N400 reflection. Now, it's hard to know exactly what the N400 reflects from a neural perspective. Perhaps it is the prefrontal cortex sending inhibitory information to the post-relonic cortices. But if we take it to be a falsification signal to semantic information, this means that even for incoming propositions with strong background clues, we will have around 300 milliseconds, or a third of a second, to disrupt falsification. This is important because we've actually found a clump of cells that faithfully track when predictions are violated. It just so happens to send dense projections to our vaulted prefrontal cortex. This is the BTA of the midbrain. Oops, the BTA of the midbrain. Moreover, in rodents, several studies have shown that the connection between the BTA and the prefrontal cortex is critical for extinction learning. The BTA is home to some very unique cells, the midbrain dopaminergic neurons. Humans have about 600,000 of these. They are large and they are complicated. They have complicated axonal arbors that are specialized to release dopamine into the extracellular space. Activity tends to be very homogeneous across these group of cells, and they project only to the anterior brain. It seems that they are well suited to broadcast a broad, unitary signal to the prefrontal cortex. Moreover, in a remarkable study by Schultz and colleagues, they showed that these dopaminergic neurons calculate both positive prediction errors by increasing their firing rates. This is when a reward cue is unexpected. And negative prediction errors by a suppression of the tonic firing rate. And negative errors here. That is, when a reward is predicted, if it doesn't arrive, these cells stop firing for a couple hundredths of a second. So what I'm claiming here is that we should see a cessation of dopaminergic firing when semantic predictions are violated. To my knowledge, this has never been tested. Okay, so this is all well and good, but doesn't explain to us how we get dopaminergic negative prediction errors. Very recent work has shown this tiny little structure at the intersection of the limbic system, the basic ganglia, the venula, is critical for the cessation of dopaminergic firing after predicted reward is omitted. Lesions to the lateral of the venula will only disrupt negative but not positive prediction errors. That is, the tonic firing rate of midbrain dopaminergic cells doesn't stop. The lateral venula sends excitatory projections to another small nucleus in the midbrain, the rostral-medial tegmental nucleus, that actively inhibits the VTA. Thus, the venulus may be a critical structure in doubt. And there are some intriguing clues to support this idea. For instance, 87% of patients with schizophrenia, a disease characterized by fixed false beliefs, that is delusions, tend to have calcification of the venula. So what's upstream of the venula? Well, this is where it gets pretty foggy. There are several recent studies arguing that the globus pallidus plays a critical role for sending information to the venula. However, these signals appear to get very complicated and more research is needed. Now, I know I'm way out of time, but I'm very quickly going to say something about the origin point of our negative prediction error. So the idea that the core function of the cortex is predictive coding has recently gained a lot of ground. And this view argues that the cortex is constantly generating hypotheses that predict sensory input at varying levels of abstraction. Prediction errors may start in the cortex when the mismatch of a prediction and experienced stimuli happen at many different levels in the hierarchical cortical structure. How cortical prediction errors influence the lateral venula still remains a big mystery here, but I think we're getting much closer than most people realize to understanding age-old questions about how we know and how we doubt the neural process of epistemology. So with that, I'll open it up to questions.
Speculating, Erik, a couple of things you suggested in your go this way, and I haven't been digging around in that literature for a while, but GABA agonists ought to accelerate extinction, yes? And dopamine agonists ought to retard it?
Yes.
Okay.
Yes. I don't know if it's that clean cut. That's certainly what we would predict in this situation. Yeah. I mean, GABA does a lot of stuff, right? Like I don't want to make it seem like this is all that GABA's doing, not only to extinction.
Any other questions? Thank you for the very interesting talk. I have a question. I'm not sure if I misunderstood, but when you presented the Pacific Atlantic example,
Yeah.
I think you said that even with strong knowledge, we have 300 milliseconds to disrupt falsification. How does that fit with the fact that you say that there is a prediction even before that? And the N400 is a reflection of a violation of that prediction. So in the representation...
Well, the argument here would be, and again, I'll fully say that this is not an accepted view, well-accepted view of the N400. There's plenty of people that argue, so it's traditionally looked at as a semantic activation, spreading of activation signal. There's plenty of reasons to think that that's not right. What I would argue here is that we do have activations happening well before even we get the stimuli. And really what this signal is measuring, this negative deflection, is really the prediction error. So maybe it's in this model, maybe it's the prefrontal cortex, sending excitatory projections to the postmortem cortices. So it's not what would be the canonical view for sure of the N400.
And I'm just wondering because if you say people predict, then they're using their knowledge already before they are comprehending the information. So knowledge comes in extremely early, and there are other studies too showing that people do predict. So you can't comprehend a true and false sentence in the same way.
Well, okay, so the argument would be here that what you're doing is you have a prediction and you have a experience.
Yeah.
Okay? And they normally conflict. But to actually produce the conflict and to even notice that they're conflicting, you have to activate all these other structures that then reject one of them. So you can disrupt that through the 400 milliseconds that it takes for that to happen. That would be what the model would argue.
I don't understand how that could work. So you make a prediction, but then you somehow disrupt noticing the violation of the prediction.
Yeah, right. So essentially you wouldn't really notice it. So you'd make the prediction, but if I could, with the prefrontal cortex patients, the argument here would be if we took out, the prefrontal cortex here, okay, that they actually still make the predictions fine. Okay? What we're disrupting is the process that's going back and going to change what's happening here, falsifying that information.
Okay. Yeah, I'm not a neuroscientist, so I don't know. But I just think it's so difficult to imagine that once knowledge is activated, you could comprehend a true or a false sentence in the same way.
I mean, again, I'll go back to the fractionation, right? Like, we hold a lot of beliefs that don't match up well to each other, right? I mean, we make errors, right? We go out and we get sunburned. We fully know the knowledge that we should wear, it's sunny out, we should wear sunscreen, but we don't activate it, we don't make that prediction. Sometimes, right? So our systems are not perfect. I think this would be a really extreme example of that, where you're just not correcting a specific incident, right?
Thank you.
That was
Great question. Thank you.
That was really interesting. So this is just a purely clarificatory question.
Yeah.
About how you see the role of the N400. So suppose that you essentially replicated the 93 Gilbert study where you had people read the sentences, some of them are marked false, but during the false sentences you have digits here that people have to indicate, right? So would you...
With prefrontal cortex patient?
No.
Oh, normal.
This would be a normal patient. So would you predict that the digit, if it appears, will be effective at causing people to accept the proposition in a way that shows up in their inferences later, if it appears up to 300 milliseconds after the sentence? And so suppose you have flash the dish half the
It
digit.
still takes time to get that information to the places that need it, right? So like, you're still delayed because of the processing that needs to take place even for that distracting information.
I see. So, but
You have to be really careful with that.
yeah, but in principle you could test this, right, behaviorally.
Sure.
See how long it takes for.
Sure.
Yeah.
Yeah,
I mean,
that's our next project. That's what we do. Yeah. EEG, and we're gonna examine it. So, yeah.
Hey, great talk. I was wondering if you could say a little bit more about the correlations between the PFC damaged patients and some of the other properties that you didn't talk about. The religious fundamentalism makes sense, but then I thought you also had some ethnic prejudice and some other...
Yeah.
And it was less clear to me how those were supposed to go together.
Yeah, so I mean, it's, we've done a couple of studies. So what we've been trying to, it's not just religious beliefs, right? So the idea is, can we get these beliefs that are out in the world that, like, normally a lot of us tend to just, that's not right. A lot of people believe it, like it exists, but so we've looked at not just prejudicial beliefs. We've looked at pseudoscientific, conspiracy, these kind of specifically suspect beliefs. And again, we see very similar patterns. Prefrontal cortex patients just are more likely to say that that's true. And again, the kind of idea here is just that these exist, we're exposed to them, and a lot of us use knowledge and other things to doubt them. And they're just not as good at normative doubt.
Yet their IQ, this is controlling for IQ, you don't see deficits in IQ that's going.
Yep, absolutely control for IQ. And education level.
Give another warm round of applause, please.
Thank you.